So this is the third part of a series of working with power meters, and in this section I'm going to build a calibrator which is similar to an HP 1163A. I've had a look on eBay at the prices of those, decided against buying one because for the amount that I use it, it's just not worth it. Using a calibrator I can provide reliable inputs to meters that I'm actually repairing, such as the 435A in the next video. So the first job is to do some research. I took a look in the Power Meter service manual, and it actually suggested using a power supply to feed into a voltage divider and to output that voltage DC into the chopper section of a spare sensor. Now, since the sensor runs at about £500, that's not really cost effective, but it does indicate in fact how the range calibrator itself works, because when you look at the diagram for the range calibrator, or you do so in the H01 modification manual, then you can actually see that literally that is what they have built. They've built a voltage divider, 12.8 volts in the top. It picks off very specific voltages, feeds them into the DC chopper, and then it basically from that point behaves exactly the same as a power sensor. And that makes sense because the power meter and the sensor go together to form a kind of hybrid device. So having concluded roughly what I'm building, here's the block diagram. I've got the line supply coming into a 12.8 volt regulated power supply. I've included from the HP options manual a switch so that you can also choose an external reference, and this will actually power the whole thing, so it doesn't even need to be plugged in, and a switch to switch the polarity of the supply as well, so you can actually test negative supply. That goes into a divider, which is literally just a string of resistors, and they are the same values as in the HP model. We go into a chopper, and I'm going to have to choose a pair of FETs for that. I might get two on the same piece of silicon. Maybe I'll just get two basic choppers to test the principle. But I will choose FETs that are designed for chopper use. The output from the chopper goes into the amplifier. Now this is going to have to match a sensor really closely. I don't know what the part number is. I know it's an NPN silicon transistor. I know that it's got a limited bandwidth, about 80 megahertz, and I suspect it's very, very low noise. Other than that, I don't know a lot. But, you know, I will source those as best I can and build it and then see where that leaves me, and I might need to make adjustments after that. So that's about it for the block diagram. Probably the only thing really is that on the right hand side we've got the standard connector, so we can actually plug in the usual HP sensor cable, because testing the sensor cable is one of the things you'd want to do with this. Okay, so block diagram's sorted, but before we can go too much further, I do need to make some decisions about the case. I can't, for example, choose switches and sockets and do PCB layout without having some physical idea about what sort of case and style this is going to be. I did find two cases that I got, this one that I'm showing on the screen and a slightly sort of narrower, stubbier one, which more closely matched the original HP size. I went for this wider one because I'm including option H01 in my build, and that means an additional switch and an additional BNC socket, and I wanted to mount all of that on the front panel, unlike the mod that HP do, which puts it on the back. I don't really want to ever have to reach behind this, so the box is fairly compact. It's 250mm wide, 76mm high, and 150 deep, so that's about 10 inches by 3 inches high by 6 inches deep. And I've sketched it out and put where I think the various components are going to go. Front panel design again. So that looks absolutely fine, and I hope you can get one of these or something similar in nature. I think it was a Hammond, but I can't see it in the catalogue. I'm dividing up the circuit board anyway so that it should fit multiple case configurations, and HP themselves just actually screw the switches into the front panel and then wire them with loose wire. So if you chose to do that, you could fit it in pretty much any case you like. The front panel draft is nothing special. It just prints out real size so that I can actually sort of just be sure that there's enough room for my fingers, enough room for connectors and all that sort of thing. But I think I just did this on PowerPoint because I happen to have that. I am working on a 4K screen because it's really helpful to work on high resolution on schematics. But this is the start. So I've got 3 schematic diagrams. The first is of the divider section, and we can see in the center there is a 10-way switch, and that goes to a number of resistors, which are essentially just joined in series surrounding the switch, and a lot of the resistances, the specification is 0.1% tolerance on all of the resistors in this divider. Now, a lot of them I've had to make up using 2 or even occasionally 3 resistors, using combinations of series and parallel resistors to get really, really close. For the smallest value, I actually bought some milliohm resistors because I also need to zero out any switch resistance that's present in the contacts. So being able to swap out, let's say, a 20 milliohm and replace it with a 10 milliohm may well be necessary. It doesn't matter quite so much once we get up to the, let's say, 10k, 50k resistors, because a few milliohms up there is well within the 0.1% precision that we're interested in terms of tolerance. But they were quite difficult to source because even the catalogues that had them didn't have much stock. There is one somewhere in here, which is a 2K2, which I've actually had to specify at 0.5%, and that's because I just could not get hold of stock at 0.1%. You'd think it'd be easy because it's a common value. I just couldn't get a 0.1% tolerance or anything better than 0.1%. Now, the bottom part of this diagram is just a load of switches. So we've got a reference in, a reference out. We've got a polarity switch. We've got whether we're in cal or standby, which basically just turns the power on or off to the divider, and an internal external switch. So these are all dual pole, dual throw. Some of them don't need to be dual pole, dual throw. They could be single pole. Okay, so that's that. Simple divider and some switch gear just to put things in order. If we go to the power supply, so the power supply is where I've deviated quite a lot from the one in the HP diagram. It's aiming at 3.8. It uses a regulator. It uses an op amp for feedback and such like. It's a bit of a pain, to be perfectly honest. Now, this isn't the best drawn diagram, but essentially we've got the line coming in through a fuse, going off to a power switch and back again. The power switch itself does have a built-in power LED, and so we're just taking that off the DC side of this circuit. So when you turn the power on, the LED comes on. Okay, and they're just here instead of a normal transformer, which is what I'd normally fit for this. I wanted things like the filtering. I wanted all the regulatory things, the common mode choke, the MOVs, etc., all the protection circuitry that you'd normally have. And I was able to just buy a part for that, which is an AC to DC regulator. It cost about £4. It contains the transformer and all protective circuitry, and the DC and a regulator, and this particular one is 15 volt. So coming out of that, I've got 15 volts. Just got a little capacitor, inductor and another capacitor forming a low pass filter, just to remove out any switching noise from this regulator, because it is a switching regulator. And then we go into the classic LM317. I did have some difficulty getting a surface mount trimmer in the range that I wanted. So we've got, this is a classic LM317 diagram. So we've got a 240 ohm, which is bog standard. Then we've got a 1K8 and a 1K trimmer, so that we're just trimming a little portion of the voltage range. This is going to give 8 to 13, 8 to 14 volts, something like that as the trim range, and this is a multi-turn trimmer, of course. Finally, we just have a little bit more capacitance on the output, just to add a bit more smoothing, and that's it. That's all she wrote for the power supply. So let's switch to the chopper amp now. I'll zoom in on this a little bit so we can see what's going on. On the left hand side, we've got the input coming in from the divider, and essentially that's switching into the chopper just here. And really what we're looking at here is the diagram of most of a power sensor. The diagram is modified slightly compared to a normal power sensor. That isn't me, that's what HP have done within their manual, so I've taken that. So for example, normally the input would come in here, we wouldn't have quite so much resistance and things like that. But basically this is a chopper, so we've got two FETs, and you can see what part number I've chosen there. It's an MMBFJ111, which is a chopper FET. There's two of them working together, and these, it doesn't matter which way around you connect the source and drain, but you know, it is what it is. 1K is on the inputs, and most of this is specified as 1 or 5%, and you know, 1% is easy to get for resistors. So output from there goes to a 3.3 microfarad. I think I've put a tantalum in for that. I might have done a ceramic, but it's one or the other. And then we've got what looks like a fairly straightforward amplifier on here, but in actual fact this amplifier is across an operational amplifier in the meter. So this is the emitter is essentially connected to the negative input of the op amp via this little feedback resistor, and the collector is connected to the positive input of the op amp, and obviously the op amp's got a little bit of biasing and things like that going on. So there we go, that's the chopper and amplifier section. I've chosen for the NPN a 2SC3837K because it seemed to be as close to what I imagined the original was in the HP, but I don't know for certain. I'm going to stick it in there, see what happens. If worse comes to worse, I will unsolder one from a power sensor, measure its characteristics, and then use that. But we'll see how it goes. Okay, let's have a look at the circuit board then. So this is the populated board. Now it's not actually meant to be used flat like this. You can do, but it's not intended to be used in this way. So you can see how that I've built it as a single board, and if I just zoom in a little bit, that the tracks themselves run through, so it's a complete working circuit. This is actually designed to be cut along these white lines. Now the only reason I didn't have my board manufacturer do the cuts is because I wasn't 100% sure that I got this right, and I'd rather on an early prototype just go for the lowest manufacturing cost. Okay, let's switch to the 2D view. There we go. So it's in 3 logical sections. The top section is designed to fit on a baseboard, and it's drilled correspondingly to these big red dots are the drill holes. We've got the fuse, we've got a big power block, which is the AC/DC converter, and you know, we've just got some connectors on this side. On the DC side then, we've just got all the components, surface mount components laid out, a little bit of a heatsink area for the LM317, and that's it really. we take them out to a couple of output plugs. So there's an output plug P8 just here, which goes across to the LED. There's a switch sockets on the left hand side, and there's P7, which is actually going to run the power to the other boards once they're separated. Okay, and it will match up with P6 on the second block of the board. So okay, so I'll just turn the polygon pause off just so we can see here. Now, so there are 3 switches set across here, and these are all spaced neatly, all the same, and there are then 2 BNCs which are underneath their relevant switches. Okay, and then down into the bottom part, so this is where most of the business is happening. So we've got the divider on the right hand side with a switch, and its output basically goes up to this little socket just here, which is going to go into the switch panel, and then the output from the switch panel comes back into this side, the left hand side of the board, where we've got the chopper and the amplifier. Now this is designed, as it says, a fixed switch on the other side. So we put the switch on the other side, and this board is separated and turned round, and so this switch is on the left hand side of the case. This socket here, IBC interboard connect 1, actually physically aligns with interboard connect 2 on this one. So once we've done that, we actually get a rotational switch, series of 3 toggle switches, all lined up very neatly on the front panel, hopefully. Now the reason it's done like that instead of being done on one single piece of board is because of the amount of space required for the circular switch. It's quite a deep switch, so actually these boards will overlap in a holder on the back of the front panel, and I didn't want any screws or anything like that on the front panel, so all this will mount from a subframe. So let's just zoom in on this section here. So here we've got the chopper input coming in and going straight into this little section just here. So the actual chopper, the 2 FETs, Q1 and Q2, and the resistors that bias the resistors that feed their gates, and the capacitors that keep them under control, etc., are all within this little section, and it has this large box around it, which is designed that should I decide to do so, I can actually solder a screen onto that. And we can see that we go into that little section, and then we have a single line coming out that takes that screen down to the chassis ground. On the left hand side we've got the PMP transistor and its surrounding capacitors and resistors, so nothing particularly special there. And then we've got the connector, which is going to go off to the 12-pin circular connector, which goes to the meter. And as I said before, the pin out on here is the same as in the actual HP design. So you know, you can literally pick up the service manual and see that cross relate all the pin outs on all of the plugs. So that's it for the circuit board. I think it's not a particularly huge board. It is 100 millimeters by 145. I do find it helpful to have a 3D model just to as a quick sanity check, really. The cutout actually in this is so because it will be where the big 12-pin socket is. And you know, I realised I needed that once I'd done the 3D model. We're going to move on to the assembly next, but I'm actually going to do that in a separate video. This is 20 minutes long already, and you know, I'll show you the main assembly steps, some of the soldering. I'll do some soldering using the oven, some using an iron, and the interconnects between the boards, the creation of the 3D plastic holders for the boards, drilling the panel, and making the front sort of decal for the panel itself. Hopefully you're going to find that interesting, but this would turn into an hour-long video if I did it all now. So hopefully you've found my sort of design process and thinking interesting? If you did, if you can give it a thumbs up or a like, and please subscribe if you haven't already done so. Take care. See you next time.